Why does a lightning bolt strike the tops of trees or the tops of buildings? Why not the bottom? Just to make it fun, let's make a big lightning strike. Let's set the charge separation to high so there are lots of excess electrons in the clouds right above our city. Let's set the cloud height as low as possible so the charges are as close to us as they can be. And to be safe, let's turn the lightning rod on so that it will protect our building's occupants from the strike. What happens when we hit play? Bang, lightning. First, some leading charges move, creating a tunnel of plasma out of the air itself, through which the rest of the charge can travel. Actual lightning strikes are much more complicated than our crude model here. The system is reset, and now we can overlay the electric field pattern. As you'd perhaps expect, the electric field pattern points from the positive charges towards the negative charges. This is the direction a free, positively charged object would accelerate. It is opposite to the direction an electron will accelerate, since it's negatively charged. The field at the tip of the lightning rod is more than 6 million volts per meter, enough to ionize air. Why is that electric field so high? Well, the electric field is greatest where the steepness of the electric potential, also known as voltage, is greatest. Let's look at the electric potential overlay. For simplicity, we made the electric potential of the ground to be at 0 volts. The clouds then, because they are negatively charged, have negative overall electric potential, nearly negative 800 million volts. Wow. The horizontal curves we see here represent regions where the electric potential is the same. These are known as equipotentials. For instance, along this line that rides over the top of the building, the electric potential is negative 40 million volts. If we overlay both the field and the potential, we can see something important. Where the equipotential lines are closest, where the potential is changing from one value to another most quickly through space, the electric field is strongest. This happens right above the lightning rod. See how close the potential lines are to one another? That means the electric field there must be strong. This idea is somewhat analogous to a contour map you might use when hiking. When you are looking at a flat contour map, circles and other shapes represent different altitudes. Where these lines are closest together, you would expect the mountain to be very steep. Likewise, where equipotentials are closest together, you'd expect the electric field to be very steep or very strong. How could we lower the electric field strength? Well, let's move the clouds farther away, let's lower the charge separation, and let's turn off the lightning rod. See how the spacing of the electric potential lines has gotten wider? Now the electric field is less strong, not strong enough to ionize air. You still get some charge motion, but not the plasma channel necessary for a strong lightning bolt discharge. We hope this simulation has been useful to you.